Welcome everyone to our online NPTEL course Environmental Chemistry and Microbiology. This course will be taught by Professor Sudha Goel and myself, Professor Anjali Pal. We are both from the Civil Engineering Department of IIT Kharagpur. We have divided this course into two parts, Environmental Chemistry and Microbiology. The environmental chemistry part will be covered by me, and the second part, environmental microbiology, will be taught by Professor Sudha Goel. This is the module 2, that is chemical equilibrium, and this is the lecture number 8. In this lecture, I will cover many important aspects of chemical equilibrium, that is the solubility product, solubility, common ion effect and the applications. We know that solubility product is very important for chemical equilibrium. All solids, we know that even if they are very insoluble, still they are to some extent they are soluble. For example, silver chloride and barium sulphate, we know very insoluble, but in contact with water they slightly dissolve and they produce the corresponding ions and they establish the following equilibriums. Okay. So, AgCl solid, this is the way to write solid. Also in some books you will see that underline is there to make you understand that it is a solid, and some part goes to solution to form the Ag plus aqueous, chloride minus aqueous. Similarly, from barium sulphate, barium 2 plus aqueous and sulphate 2 minus aqueous. Now, we already know the equilibrium expression how to develop. So, for equation 1 we can write that K is equals to silver plus ion concentration, that is aqueous phase, into chloride ion concentration in aqueous phase by silver chloride in the solid phase, the concentration of silver chloride in the solid phase. So, this one we know that I have shown you the rules to be followed in the chemical equilibrium. So, this is a constant because this is solid. So, this is a constant, and then K is, if you place this is a constant, then in that case KSP, we call it KSP. So, KSP is, so basically AgCl, this constant will go this side, K into K dash, say for example, that will be KSP, and this is nothing but silver plus ion concentration into chloride ion concentration. K is called solubility product. We have seen that different ways we can express the equilibrium constant. Say for example, in case of acid dissociation we write Ka, in case of base dissociation we write weak base Kb, in case of water dissociation we write Kw. Here also that way we write, this is also equilibrium constant, but we call it solubility product and we express in this way Ksp. This is a very important term actually for chemical equilibrium. It is constant, it is a constant at a particular temperature. All equilibrium constants are constants at a particular temperature. In almost all textbooks or handbooks dealing with qualitative and quantitative analysis, the solubility product values are available. You can see it as a list, they show at 25 degree centigrade what is the solubility product values. In a similar way, for a complex salt such as, this is a very simple formula, AgCl, barium sulphate. So, to develop the equilibrium expression is very easy, but for a salt like this Ca3PO4 calcium phosphate, Ca3PO4 twice, how to develop the equilibrium expression, that has been shown. So, 1 mole of calcium phosphate produces 3 moles of calcium 2 plus and 2 moles of phosphate 3 minus. So, in that case Ksp will be calcium 2 plus concentration to the power 3 into phosphate ion concentration to the power 2, because here the stoichiometry is 3 and 2, that is why it comes as a power. Now, this is very important, this is solubility. Okay. So, in the previous slide you have seen the solubility product, here we will see what is solubility. Okay. So, here you see that barium sulphate, if we take this particular example, barium sulphate goes to barium 2 plus aqueous plus sulphate 2 minus aqueous. Now, we know that solubility product of barium sulphate at 25 degrees centigrade, this value is given in some books, in textbooks. So, it is nothing but 1:10 to the power minus 10. Now, if the solubility is S, if the solubility of barium sulphate is S, for example, then the concentration of barium 2 plus will also be S and concentration of sulphate 2 minus is also S. So, from the equilibrium expression of barium sulphate we can write that Ksp is S into S, that is this value which you can obtain from textbooks. Now, then what is S? S is the solubility. So, S is nothing but 1:10 to the minus 5. This is the solubility of barium sulphate. This is a very simple case, but in case of calcium fluoride, say for example, so from 1 mole of calcium fluoride we get 1 mole of calcium 2 plus and 2 moles of fluoride minus. So, equilibrium expression if we write, then Ksp is nothing but S into 2S to the power 2. That means the S is the solubility. So, here it comes Ksp is 4S cube, which we can get the Ksp value from any book. This is nothing but 3 into 10 to the power 11. So, if you see these two solubility product values, then here the barium sulphate solubility product is in the order of 10 to the power minus 10, but here it is 10 to the power minus 11. Okay. So, here it is higher value, here it is lower value, but just by looking at the solubility product values and comparing, we cannot say who is more soluble and who is less soluble. So, for example, here if we solve this, then we will get that solubility of calcium fluoride is nothing but 19.6, this is almost 20 into 10 to the minus 5, but here the solubility is 10 to the power minus 5. So, here it is 20 times higher than this one. So, although solubility product of barium sulphate is higher compared to calcium fluoride, but solubility of calcium fluoride is higher compared to barium sulphate. So, it can be said that calcium fluoride is 20 times more soluble than barium sulphate. So, looking at the solubility product immediately without thinking we can tell that okay, whose solubility product is higher. So, this is more soluble, but it is not like that. Now, understanding the phenomena of precipitation, we know that what is saturated solution, what is unsaturated solution and what is supersaturated solution. What is unsaturated solution? Taking a simple example, we can write that it is AB. So, A plus concentration into B minus concentration. If it is less than the solubility product of AB, then it is an unsaturated solution. Once the Ksp is reached by this, then it will become a saturated solution. When it just reaches the Ksp, it is a saturated solution. But when it goes under certain conditions, the A plus concentration into B minus concentration, this can be higher than the Ksp, like this. You see here, then this solution is a supersaturated solution. Okay. And in the supersaturated solution, sometimes we see that if we disturb it little bit, then this AB in this case, it will immediately precipitate to some extent to become just the saturated solution. This we can see in crystallization also. Say for example, if you want to make some crystals, okay, of something, say for example, sodium chloride. So, you make, or say sugar, okay. So, you make a very saturated solution, and then very saturated means almost supersaturated solution. Then you put a single crystal of that material, then you will see lot of crystals are coming. That is called seeding. Okay. So, this thing happens, that means you are disturbing the supersaturated solution, so that it will try to remove some crystal, some salt from there to get just the saturated solution. Now, this is common ion effect on solubility, very important. Say for example, we have a electrolyte Ba whose solubility is S moles per liter, okay, Ba, you see, which will give B plus plus A minus, okay, and the solubility is S moles per liter. Now, there another electrolyte say Ca. What is interesting feature here? In Ba and Ca both, this is the common thing, A minus is common. So in Ba solution, where the solubility is S moles per liter, we are adding another electrolyte which is Ca, okay, and A minus is common. Then what will happen? Okay. In that case, you see, initially when it was alone, then solubility is S means Ksp is S square, but now we are adding Ca, and what is the concentration of Ca? This is the C moles per liter. Then after adding Ca, the solubility will no more be S, okay. It will change. How it will be changed? Because the concentration of A minus is now higher, it is now S. If the new solubility is S dash, then it is S dash plus C. So, it is higher than S, okay. So, when it is higher, then S dash should be lower to keep the Ksp constant, that means the solubility will be lowered, okay. So, common ion effect means you are adding a common ion, then the solubility of the original electrolyte will go down, okay, resulting in the decrease in its solubility, and the new solubility of Ba is S dash. So, I explained already this thing. The solubility of an electrolyte is thus decreased by the presence of a common ion. However, the solubility product remains the constant. So, one important question I have given here, how to get pure sodium chloride precipitate from a solution of a sodium chloride solution. How you will do it? You take the concentrated sodium chloride solution, okay, and then you pass HCl gas through it. So, what you are doing? In sodium chloride solution, chloride is common. Now, you are passing HCl where you are adding a common ion which is nothing but chloride ion. So, what will happen? The some sodium will go out of the phase. So, it will be precipitated as sodium chloride. So, you will get pure sodium chloride as a precipitate. Now, common ion effect on solubility, I have already told you what will happen if you add a common ion to some electrolyte. Okay. Now, here is it is the quantitative approach, it is shown here, it is the example is given with barium sulphate. Say for example, I have already explained that barium sulphate, the solubility is 1 into 10 to the minus 5 molar. Okay. Now, if barium 2 plus, say for example, barium chloride I am adding, it is increased by addition of outside source, say for example, barium chloride. So, some concentration was already there, now we are adding some extra barium ion concentration, that is through the application of barium chloride. Barium chloride is strong electrolyte, so it will dissociate completely. Then what will happen? What will happen to the barium sulphate? Okay, that is shown here. Now, Ksp is constant, Ksp is nothing but this, can be given by this expression, and barium sulphate also this is the equilibrium expression, this is the equilibrium reaction. Okay. Now, what we have done? For example, let us assume that we have added barium chloride in this concentration we have added, okay, 10 into 10 to the minus 5 moles per liter is added to the above solution. This will cause in the formation of an additional Y moles of precipitated barium sulphate. When the barium concentration will be increased, then what will happen? Some barium concentration, some barium sulphate has to be going out of phase, okay. Some barium sulphate should be precipitated, but how much? How much will be precipitated? And when barium sulphate is precipitated, then sulphate ion concentration will also go down, but how much? That we want to see. Okay. This is the new in the new expression, this is the concentration. So, it was originally there for barium, now we are adding this one and now some amount of barium sulphate is precipitated. So, that is Y. Okay. So, here it is also Y. Now, what is happening to sulphate concentration? It was originally there, now Y concentration is going out. So, this is the final concentration. Now, if we put it in the equilibrium expression, then Ksp is nothing but barium ion concentration, this is nothing but 10 plus 1. So, 11 into 10 to the minus 5 minus Y into this sulphate ion concentration, this is the new concentration. So, this one and this is the solubility product. So, if you solve this, then you will see that Y is nothing but 0.9 into 10 to the minus 5 moles per liter. Okay. So, what is the final concentration then? For barium it is this minus Y, that means after solving this is the 10.1 into 10 to the minus 5 moles per liter. What is the concentration of sulphate now? Final concentration, this is 0.1 into 10 to the minus 5 molar. Originally how much? Originally it was 1 into 10 to the minus 5 molar, but after adding barium chloride it is reduced almost 10 times. So, it is observed that sulphate ion concentration is reduced considerably. This is an application of common ion effect. So, when the sulphate ion concentration is reduced, that means lot of barium sulphate has been precipitated. So, in this way sulphate determination is done by adding enough excess amount of barium chloride, so that almost all sulphate ion is precipitated as barium sulphate. Okay. This is used extensively in environmental engineering practice and in analytical chemistry to accomplish complete precipitation of the desired ions. This is also true for hardness removal. As I told you, from the outside we are adding some carbonate or hydroxide to get precipitate the calcium carbonate and magnesium hydroxide to remove the hardness. Now, common ion effect on ionization, this is general thing, but we have seen in buffer also, ammonium hydroxide, ammonium chloride buffer or acetic acid acetate ion buffer. So, what is happening here? The ionization of a weak electrolyte, a weak acid or a base, in this case it is the ammonium hydroxide, in this case it is the acetic acid, in solution is suppressed in presence of largely ionized salt having a common ion. That means, in this case ammonium chloride if we add, then this is the common ion. So, common ion means when this concentration is increased, then what will happen? The to keep the Kb constant, ammonium hydroxide should be dissociated even less. Okay. Then what will happen? We can control the concentration of OH minus. In this case also, if we add acetate ion, then we can control the dissociation of acetic acid. In that way we can control the H plus ion concentration. The larger the quantity of added salt, the smaller the ionization of weak electron. If we increase the concentration of ammonium chloride, still it will be less dissociated. Okay. So, dissociation will be still lesser. Okay. If we increase this concentration, then the acetic acid will be dissociated even in less concentration. Okay. So, the degree of dissociation will be less. Okay. Thus, the common ion effect affords a method for controlling the concentration of ions furnished by a weak electrolyte. So, this has enormous applications in many cases. Say for example, in group separation, those who are in chemistry background, they will see it in group separation. What is there? Here all the sulphide salts are considered. You can see here mercury sulphide and copper sulphide and cadmium sulphide. You see the solubility product, you can see here it is so less, it is very insoluble compared to this zinc sulphide and manganese sulphide. Okay. So, what is happening? On passing H2S gas into a solution of salts of these metals, the metal sulphides will precipitate when only when M2 plus ion concentration into sulphide ion concentration exceeds the solubility product, that is Ksp. This we have seen already, that the saturated solution, unsaturated solution and supersaturated solution, only when this will reach the Ksp value, then only they will be precipitated. Now, in case of H2S, we see, if we consider this equation, then we will see that here the a saturated solution of H2S is 0.1 molar at 25 degree centigrade, and the concentration of sulphide ion it produces is can be written in this way. From the equilibrium expression it can be written in this way. Now, if we increase the H plus ion concentration, that means if we consider the acidic solution, when this is increased, then this concentration is much less, sulphide ion concentration should be much less, and at that concentration only those sulphides, those metal sulphides will be precipitated who has very low solubility product value. This will not be precipitated, but this will be precipitated. So, in under acidic condition and acidic conditions, because sulphide ion concentration is less, so only this will be precipitated. If you have a mixture of all these, then sulphides of only these three metals will be precipitated under acidic condition when you pass the H2S gas. Okay. But the other this will not be precipitated, and they are precipitated while FeS, ZnS, MnS etc. will remain in solution. They will remain in solution, but they will precipitate. Okay. This is an elegant demonstration of solubility product and common ion effect, which has been used in group separation in analytical chemistry. Now, chemical equilibrium, this is a very simple examples to understand what is solubility and what is solubility product. Here it is given silver chromate Ag2CrO4 is red solid that dissolves in water to the extent of atto gram per liter at 25 degree centigrade. Then what is the Ksp value? It is very simple. You have to first set up the equilibrium expression, then set up the equation, balanced equation, then set up the equilibrium expression, then you find out the here you have seen that this is grams per liter. So, you have to express in moles per liter, this is the unit moles per liter, and then you have to put it in the Ksp value, because Ksp is to know the Ksp we need to have the solubility values. You put the solubility values in the expression and then you get the Ksp value, which is nothing but 10 to the minus 12 order of 10 to the minus 12. Now, as the conclusion we can say that in this lecture it has been explained how electrolytic dissociation enable us to determine the conditions under which a substance dissolves or forms the precipitate. So, solubility product is the key factor that will tell you whether under which condition it will precipitate, but Ksp value is constant, but solubility you can vary by adding either common ion or without adding common ion. You can change the solubility, which we need to know whether it is in solution phase or it has to be precipitated out. Okay. So, it is a very important thing to know in chemical equilibrium, in process engineering or in environmental engineering or in analytical chemistry, what is the concept of solubility product and solubility and what is the common ion effect. Thank you.